Good morning, everybody. Welcome. It's good to see you all. Stockholm is unusually warm. It's, it's good. It's sunny, but I guess at least some of you coming from the Nordic countries will find this quite unique. I'm going to talk this morning about a topic on how to use machine learning for understand the physics around magnetosphere, Earth magnetosphere. This first talk is meant to give you more high level intuition on how this works, what are the major technique, and what are the best approach. How you should frame your machine learning project for studying magnetospheric physics in a meaningful way. Right? There's a lot of tendency of basically taking tools or using some large language model and go there deploying without having like a step, without actually spending some time to understand, okay, what is the best method? What is was actually the problem that I want to solve? Somehow, everything is too fast today. So the software environment became quite cheap with using the LLM. So one thing that I want also to make the point today is really that the fact that software becomes so cheap doesn't mean that we should rush up and basically taking a tool, deploy, and get some results, right? On the other hand, it makes your position, your domain-specific knowledge much more important, right? So the value that you have is actually an understanding of the space physics, understanding of that particular problem that you have. The technique that I explain, I introduce now, are basically tools for you, right? So the value that you're having is actually taking a tool, working, and assessing critically to ensure that there is a loop coming from the input data to the results to actually validation, understanding, and interpretation. So the major value that you bring here on the table is actually interpretation and your physical intuition of what's going on. Does it make sense? Does it not make sense? And if so, are you looking at something new, or is really what you expect? The main point of this lecture is that machine learning is not a replacement for space physics or your understanding of space physics. It's not going to bring you to any scientific discovery if yourself are not leading the process itself. So this is one of the major message that you should have by the end of this lecture. These are tools. It's important to have understanding of the tools, but makes even your background, your knowledge much more important, right? So you're responsible to bring it to the next level. Magnetospheric physics is challenging. You don't have me and myself here today to tell you how difficult it is, right? There are three fundamental reasons. The first one is really the fact that this is a complex system with a highly variable driver. So you have the coupling coming from the sun, and all the plasma coming out of the sun, and more or less extreme events that come from the sun, and interaction of solar wind with Earth magnetic dipole, an internal plasma environment of the Earth magnetosphere. So any big challenges that coming from the sun, is propagating through space and impact the magnetosphere. So this has impact both at microscopic level, also may trigger local wave interaction, turbulence, magnetic connection. Some events that extremely localized in space. We're talking about electron scale, a few ion skin depth of length, but also this is coupled to the global dynamics of the system. Yesterday, I mentioned, for instance, how a highly localized phenomenon like a magnetic connection can affect basically all the global dynamics of the magnetosphere, changing the overall topology and triggering storm and substorm. So how this microscopic and macroscopic couple is a major research question, right? Some of you probably have been working on this. From modeling perspective, you want to model from kinetic scale, all right, and then go up. However, kinetic scale are too expensive to go. So you always need somehow fluid models, more MHD like modeling in order to assess the dynamic of the full system. However, there is a big channel, right, in a channel of energy momentum transfer from the lower scale to the global scale. If you do the global scale, then you cannot do it. You're missing some of the kinetic physics that is enabling for instance, a magnetic reconnection. The data that we are in a unique position that whenever you look at the plasma physics problem from data perspective, we are somehow in a privileged position because we have both data today from kinetic scale, so you can have data from coming from distribution function to more global information such as the moments of the distribution function, density, bulk velocity, pressures, temperature, right? So we have also in the data this double perspective, different scale. So we have the very same problem that we are having in modeling. So how you do how you do the analysis of data? Are you going to use kinetic scale data, for instance, distribution function? Are you going to use momenta? Are you going to use some very high-level predictor dynamics, for instance, DST index or some space weather index? So at which point of the hierarchy you want to put yourself? So if you have done a little bit of modeling, here there is exactly the same issue, right? So you have very diverse data, very heterogeneous, but most importantly for you as a physicist or as an engineer, you have data that belongs to different hierarchy of the system, maybe kinetic, maybe fluid. It can be even a higher, more phenomenological, like a DST index. When it comes to data, also there is a very, very peculiar uniqueness of space data as coming from the fact that the data is only sampled in some particular area of the orbits of the spacecraft. So whenever you have a mission, either ESA or NASA mission, you have some research question, and then you have an engineer and scientist, space scientists designing specifically orbits for studying a specific event, right? So then, if you are after a certain phenomena, you know the certain phenomena is very likely to happen in certain region of space. So you design the orbits of your spacecraft so they spend as much as possible time in those areas where you might encounter the phenomena that you want to do it. So all the orbits that have been designed are basically designed for a specific research question that is going after a certain particular phenomena that you want to study. So the orbit itself is designed for that. Not only that, but also the sampling, how you want to turn it on the detector, the different instruments is depending on what you want to study. So if your spacecraft is an interesting area, you basically turn it off. All your instruments, you don't do any sampling. As soon as you go in an area that you want to study, not only you just have sampling, but also you can increase the rate of the sampling to have even much higher sampling. So this brings a very important problem, which is that, first of all, your data is rather sparse, so it's only along certain lines, certain paths, and also is only in certain area that the research scientists, when designing the space mission, decided that they wanted to have. So the major problem that you're having when using data for space is that you have extremely skewed data in some region of space, which is discrete, so only in certain point of the space. And you're after in reconstructing the full 3D. So instead of following just the path of the spacecraft, you want the full 3D perspective, reconstructed from very sparse data, and also you want to have the dimension of the time, right? So how does it change in time? So these are the major three challenges when it comes to data. I just want to spend a few words. If you're not from magnetospheric physics, then what is the system that we are applying? As I mentioned today, we have we start from the sun, our stars, that is emitting a so-called solar wind that is propagating to the space. Propagating through space, he has attached the solar wind a magnetic field, the so-called IMF. So this at this point, the solar wind is behaving like pure MHD. You can think as the magnetic field is convected by the solar wind. It might have typically northward or southward or some direction. This has an impact on how it interacts with the magnetic dipole. And some configuration are more amenable to magnetic reconnection. So we have the solar wind is impinging with certain properties in terms of the distribution function, in terms of density, in terms of velocity. Is impinging on the magnetic dipole, creating so-called bow shock. So this is a shock, as we have in real life. Shock you can think as like a big discontinuity. Is very particularly is probably not a fluid shock like we have in normal fluids, by so-called collisionless. It means that collision are not do not occur in time scale of the shock formation. These are some particularities. I'm not going to detail, but for the lecture today, you can think that the encountering of the solar wind with the magnetic field coming from of the dipole of the Earth created this big discontinuity. In connection to this continuity, you see very interesting stuff. You might have some population of the plasma that is reflected back, very much like in a shock. Some of the plasma that is going through the bow shock and is basically heated up. So you might think if you have a very peak you have a very peak distribution going through the shock. The part of population goes through the top, basically get like a temperature, right? So get some thermalization. Some of the particles get accelerated by reflection. There is typically quite a lot of turbulence associated to this region. So is a fantastic and beautiful system to study, maybe some of you, and is one also the system for which machine learning has been used the most to find out where actually your data is showing a bow shock, right, and find out which processes are associated with the bow shock. So one of the major applications is to find and characterize this bow shock. The region, coming from the sun after the bow shock, the region after that is called magnetosit, that consists of the population of plasma coming from the solar wind that has been heated. Depending on the orientation of this magnetic field that the solar wind drag, your population, this magnetosit population, might or might not be turbulent. So you might have in certain kind of configuration that is highly turbulent. So if you're looking, for instance, your research study looking at what is the structure of a collisionist turbulence, what is the structure of a wave particle interaction, this is one of the most beautiful special laboratory to study this kind of experiments. It might or it might not turbulent. There are also sometimes a certain configuration of the system where it is not turbulent, but in many cases is highly turbulent. So that makes particularly interesting for people who are looking at wave particle interaction. After magnetosheet, there is a boundary layer, very important boundary layer between the shock plasma after the Bohr shock and the inner magnetosphere part of the Earth. So this is called magnetopause. And some of you probably know why the magnetopause is important. Magnetopause is one of those regions where people are looking for magnetic reconnection at their side. So you have a very symmetric configuration. So you have different intensity, different magnetic field. And then you have this boundary layer where very likely is the region where you are looking for magnetic reconnection. So for instance, most of the mission on studying magnetic reconnection, they tend to spend a lot of time. There are some empirical models that tell you where is likely to be at this boundary layer. So the mission itself is typically designed to spend as much as time possible in close to the magnetopause, right, to this boundary layer, and that tell you, what is the impact of the data, right? If you are, for instance, want to study the Bohr shock using some mission for studying magnetic reconnection, yes, you will have chance to have events, and that's what people do it. But most of the sampling will be in a very specific area. So it will be in very close to the magnetopause. In the tail is also very interesting. So the effect of solar wind coming, impinging on the dipole of the Earth is compressing in a shock the day side, and then elongate on the tail, right? If you think from just MHD perspective, you have the plasma that is dragging the magnetic field and is extending them on the tail. This is also quite interesting area. Most importantly for magnetic reconnection, which happens in the tail here in the back, and that leads to a regularization of the topology of the Earth magnetic field. So the important part when you're looking at this from a data perspective is to recognize that all these different regions have a very different distribution, right? So if you take, for instance, the region, this region here, the solar wind, you might expect, if you look, for instance, at the ions and the protons distribution, and you take, you measure the distribution, you want to say what is the distribution in the density, you will find that very likely like a Gaussian. It will very likely also that this Gaussian will have a certain width. The width, if you probably remember, is basically related to the temperature. If you have higher temperature, it will be a higher width, and so you can infer quite a lot, right? So the most important thing is to understand that if you take ion distribution here, we'll have a certain configuration, the density with some Gaussian distribution on some position with a certain width. If you take the ion distribution here, it will be quite different. Major reason is This is after the shock, right? So there will be heating. So the Gaussian itself will basically much larger. So as a scientist, you can already think yourself, right? You have some very strong signal how you could design a method to identify it automatically. It turns out that many of these machine learning techniques are very basic technique that look at the different distribution function and put together those distribution function that look similar. Mm-hmm. The beauty of machine learning is that they're very good in handling high-dimensional space. What it means, high-dimensional space? Well, as a human, we probably can handle density, velocity. Well, we look at the shape and we say, okay, these look different, right? But if you want to handle the data coming from the space, easily you have 20 different quantities. Mm-hmm. So it's difficult for a human. Probably some very advanced chess player can actually do it to extrapolate it to very high dimension. But if you didn't train yourself to read 14 plots in a row and understanding what are the difference, you might want to seek some guidance from machine learning. Mm-hmm. What I mean guidance, so you start from this 20 feature, you let the machine learning understanding which distribution is different, and then you go back, right? You ask machine learning to tell you, right, what are the characteristic distribution function. You look at the distribution function and you interpret the distribution function. So it's important that you realize to that. Fundamentally, what we're going to, when you're working as a data scientist on space physics, you are looking at, try to understand distribution function in certain quantity, where these quantities in data scientist language are called features. You also always hear about features. It's nothing particularly difficult. If you decide that you want to study distribution function of the density, velocity, the density will be one feature, the velocity will be another one. There are also some technique basically to reduce your feature from the physical space to some compressed feature. Somehow they bring the same information, but are not directly interpretable. So these are also called latent variables. So somehow are basically a proxy of a different feature that are correlated. So they compress all information of the multiple features. The downside is that they're not directly interpretable, right? So you need to go back from this latent space to the physical space for yourself to handle. Turns out that the less number of features you have, the easier is actually to do automatic classification, automatic machine learning. So it's typically quite good step, going through the physical space to this compressed space, which does not have direct physical interpretation worked there, and then go back to the physical space for interpretation. The most important things when you work on a data machine learning project for space physics is to make it physics-driven, right? As a space physicist, as a space engineer, you have basically no value, just take it and apply and get something out. So the first thing you need to ask yourself is what you're after as a researcher in your particular field. There are basically 6 different areas that as a scientist you might be interested. The first is I'm actually interested in making a climate map of a certain magnetosphere. What does it mean, a climate map? I want to know what are the different regions in space. I want to know, for instance, we know quite well the Earth magnetosphere, but let's say that you want to study a different magnetosphere, like Mercury with the Bepi Colombo. and you want to see if there are any particular region that is not known, as not well characterized. So then what you want to do, you want to have as much as data. You might want also to have some technique to go from very sparse data along some trajectory to more volumetric data that give you, the more the 3D pictures. And then you want to have a method basically to assign to each of these grid points some feature, for instance, information about the density, distribution function, and temperature. You want to ingest on the machine learning part to basically find automatically what are the characteristics different region. You typically do after some pre-processing of your data. You go from physical space to some low-dimensional space through some technique. You do the analysis there, and you find the different classes, and then after that you go back. And that point is where the most rewarding part of from your side. What actually does it mean? What this method is doing? Is me tell me something new? Most of the time, I'm quite pleased when running this, because it's very nice. It's very nice when you recover all existing results. From as a researcher, you would like to see something new. From say, okay, I find it something new, and so for some of you might be disappointing, but myself, I found very reassuring that 50, 60 years of the space physics are coming back in the physics, and you find the data evidence, right? So you can actually go way beyond the some physical model. So this is actually the reality. So you might want to study regions. You might want to study. Probably the most interesting part is actually transition between different plasma distribution, because all the interesting physics happens between transition, right? You might have Bosch-Yock, you might have boundary layers, you might have all the magnetic reconnection. They all occur when you have some jump in certain quantities. So as a scientist, you might want to study, where is it coming, how is actually evolving in time, this transition. It might be, your research question might be a simple phenomenon, right? It might be a working magnetic reconnection. What is my field? Magnetic reconnection, wave particle interaction, turbulence, right? It might be the dynamics, storms, substorm injection. So you might want to step back, right? And you might want to also to use some space weather index to augment your data, right? You have the spacecraft, but then you have a bunch of other indicators that you can have here on the ground that tell you how the magnetic field of the Earth reacted to some event. You might want to interested to kinetic physics, right? So how particle behave, right? So the most fundamental question in the universe is how particles are basically accelerated, right, in plasma. So you might be after something more fundamental, and you might also interested in transition, like more space weather events, when the big storm happens. What are the big changes in the topology? The important point of this slide is to make this very strong point today that whenever you start a machine learning project, you must know on which of this category you do it. If it's not clear what you're after, then you need to step it back. The reason for that is that any of these different topics might need a different machine learning approach. The typical approach, you take the data, you take some neural network, you get some label data, you do something, right? That's not what we do as a researcher. We define first on one of these 6 categories we are belonging, right? And then we drive the method itself, coming from the science part. I want to spend a few words about the problem of scarcity. I don't spend much time because I already spent quite a lot of time at the beginning talking about the problem. But the problem is the following: you have this blue trajectory here, and you have a mission that has been designed for study certain phenomena. For instance, if you heard about the NASA MMS mission, which is a magnetic connection mission, has been designed to spend most of the time here on the equatorial plane, right? So most of the data will be here. Also been designed to turn it on. So it has different phase, phase 1, 2. Phase 1 that basically sample this region here, the day side. So the sun is here, and it turns on all the instrument here. This particular is so you have sampling. When you go, here, it basically you don't. Sometimes they turn it on, but most of the time you have no data. After that, then this is the phase 1, and phase 2 is mostly spend time here. It means that it's spending most of the sampling time on the magneto tail. So the problem you have is that you basically have time series corresponding to some quantity. So you have your instrument. You have instrument to calculate the density, instrument to calculate magnetic field, the instrument to calculate the temperature, and you might have some data that looks like this. For you, it looks like a time series, but in reality, is actually the sampling in different position of the space. So the very first step is basically, if you want to do some pre-processing, is to go from the time dimension to the space, right? So you know where most of the oscillator devices, they tell you exactly where they are, the space where they are, so you can recover the position. But what appears as a time series is nothing else than a sampling of certain quantities of certain feature in certain position of the space, which is sparse, and also is highly skewed in certain region of interest for the mission itself. Also, this is experimental data, so these are instruments that might be affected by noise. Some part of the device might not be useful at a certain point. Something might happen. And most of the post-processed data, they will tell you if there's a problem, but you still might have some of the anomaly that coming actually from the device itself instead of the physics. If you're lucky, in your space project, you have labeled data. What does it mean? It means that you have a certain configuration, for a space, for your feature. For instance, you have information about the density, temperature, bulk velocity, all these quantities, and then you have a label. For instance, you have a label that say magnetospheric, right? Or you have a label that say turbulence. So these are so-called label data set, right? There are very few because you actually need today humans to go through to the data, interpret the data, and then put, okay, this is turbulence, quiet, turbulence, wave particle collection, magnetic connection. So you need to spend quite a lot of time. And also, it's very difficult to put, make a scientist and physicists agree on something. And so you might have a lot of questions. Okay, is actually real magnetic connection? No. Is really turbulence? No. So most of these label data also have quite a lot of debate across. If you put together 2 or 3 space physicists, it will tell you probably different things, right? There are super clear events that all the space physicists will agree, but it turns out the most interesting events, they are very, very critical to analyze. So you might have label data. You might also have most of the label data that you have is ambiguous, right? So that's that comes from some particular human choice. So if you are using also this particular kind of data set, you need to take into account that the labeling part is a source of error itself. So you might have. So where, as a space physicist, the machine learning comes up? Well, it's important for you to understand that machine learning itself is a workflow, right? So he has quite a few step by step. It is a very engineering tedious work, right? But some of this engineering work that you need to do with discipline, because otherwise it's very easy that you don't get something that is meaningful out. You start first from getting the data, understand what is your data set, what are the units, what are the reference system, have a very good grasp of your data set. The second major step is massaging your data, right? If you are one particular process, one particular research question, you need to understand which data is most informative for you. Obviously, you can start from taking everything, right, all the data, but you will need to put yourself understanding, okay, which feature are going to be the most important one. There are techniques to understand, given a certain phenomena, which are the features that are most important. You can go from very basic statistical analysis tool, like a correlation on certain phenomena, to more advanced technique using neural network and studying uncertainty quantification. Nevertheless, it must be very clear to you already before stepping in your machine learning project which kind of data you most likely you will get the information. After you have data, you as I said, you understand how to represent your plasma state or how to represent your events state. Let's say that you want to study one is the turbulence or no turbulence, you will need to find a way to say, well, do I take just one snapshot, right? I take all the quantities at a certain position, or I decide to take, 2 minutes of sampling, and then I take an average, and then I take the standard deviation. It's up to you. It's up to you to decide. But these are critical questions for you when you prepare your data set. Let's say that you want to take a time window, right? And then you take all your density, temperature, when you take an average of this and associate with that window, how long you should take the window. You probably take a window that is large enough to include, for instance, a bow-shock crossing if you are after bow-shock, but not big enough that everything got diluted, right? So you need to think quite hard how you want to data. You take just one snapshot here. I take a window of my distribution, and then that is going to be my state. Then it comes more like engineering work, the machine learning methods. So this is a rather standard technique that you will learn this week. And then probably the most important part is this output here, right? So that's actually when you actually to jump in. You get the data, you get some information out, and now you need to interpret. That's the most exciting part from your side. There are often some post-processing part that you need to do. As I told you, you need to go sometimes from a compressed representation of your feature back to the physical feature space. And once you have the feature space, then you can interpret the method. There are different applications right? So depending on what is your research question, you might be after one of these 5 prototype application, right? Most of the people focus on this one. Most of the time, whenever you have some machine learning, people go for classification. This is obvious. This is probably the first project anybody do when doing machine learning, right? It's easy. You have some label, but basically taking the distribution function, right? And depending on the time or the space, telling if this region is belonging to magnetostate, this belongs to the magnetopause, and this purple one from magnetosphere. So just take some measure, and then you just give input a certain point or a certain time window. What is the values of the density, temperature, bulk velocity, and then you get out one of these discrete label, right? I'm in magnetostate. I'm in the inner magnetostate. So this is probably the first one, the obvious one. Pretty much everybody is doing it. Much more interesting and more towards the scientific discovery itself. You have some unlabeled data. You have distribution in space, and then you use some technique to automatically put together those states that have a similar distribution in this very high dimensional space. So this is automatic. So then you have this algorithm, and then is your task to go back understanding what actually each cluster means. Because the method itself is just doing the cluster for you. Once you have distribution, so you basically have a cluster, you basically have a very, very strong information. You basically have information of the characteristics distribution function in the magnetosphere. So a picture like this is extremely important, right? Because you see where the major distribution are. So all these points, they have a very similar distribution function, distribution in this highly dimensional space. If you have a point that is here, that is a so-called auto-distribution event. So you have a very, very powerful technique to basically say, well, if something is auto-distribution, it does not belong to any of those clusters, must be something special, right? Most of the time is an instrument that doesn't work. Most of the time it might be some events that by chance was detected by one of the instrument. Some of these very rare events, it happens. So you can use your technique as anomaly detection. You can use probably the most application side is you can use to do prediction. If you're working on space weather, you will see on Thursday, I think, or on Wednesday, you can use information of the imaging, for instance, for the sun to do a prediction on what is going to be the impact of a solar storm on the Earth magnetosphere. For instance, you can use imaging to predict what is going to be the DST, the disturbed storm index. So this is also a quite popular application of machine learning prediction. And one other application you might have a so-called gap filling or in painting. If you have some measure and you're missing some information, you can ask your machine learning or neural network to basically fill it for you, depending on the previous statistical information that you have in the data. It's a sort of interpolation, right? But more sophisticated. You can also put in this kind of interpolation some physics on it. But bottom line, it's very likely that your machine learning project will be one of these 5. So remember, you go first. You start first from the science. You understand the workflow. You do it. And the workload will depend on which kind of research question you do and which one of these methods you're going to use. I'm running out of time. I just want to give you an example of how this could work in practice. You have the data coming from, for instance, MMS, right? So you have one spacecraft, you have 4, you can pick up 1, and then at each time you can get information about magnetic field. You can bulk velocity, temperature. What you're going to do? You're going to use some dimensionality reduction. So instead of having 14 quantities, you can reduce safely to 5 or 6. To 5 or 6 that retain all the original information. So they still have a connection to the original information. They retain most of it. And you can also order in terms of importance. Say which of these artificial latent new features that I created through PCA is more important than the other one. So you can make the first feature, the second, and the third, right? Depending on the importance. Then you can make a plot, right? So you have on the x-axis you have this dimension in the lattice space, and then in the y-axis, unfortunately, here is a cut. Is the second dimension. So these are kind of artificial latent space. Each of your point, right, that will basically project it on this plane. And what might happen is typically happen is this pedagogical example where the cluster are very divided. You will find that many quantities are basically clustering all together. At the first step, you will, if you do this exercise, you will find this, but you won't have any of this information, right? So what you need to do is to do this validation step, going back from the lattice space. So you look, what is the typical distribution for your physical features? So in this case, I start from MMS. I say we have 12 different classes. So automatically you get these different classes, and it gives me index from 0 to 11. But there's no physics. Now is where I jump in. I take the first cluster, and what I do, I take all these points and then calculate. For instance, where is the position in space, the density, temperature, velocity. And by looking at this and putting my knowledge about space physics, I can do interpretation about what is the different class. So this is the final interpretation step that you will need to do it. So I finish up here. And so conclusion, always frame your project as a space physics first project, right? So that's where is your where the value is going to come from you. This technique are rather basic for you. Most of them you can be just some statistical learning technique. There is no black magic, right? So if you have been familiar with statistics, that it is. Some of the techniques, they work more black box, but it's important for you to bring all the knowledge and close this cycle. That's it from my side today. Thank you very much.